Right. My dear, ke batla fela re qetelle taba ya the ideal gas. Unfortunately, you were not in class when we dealt with many of the fundamentals that governs the behavior and the properties of the gases. I think I'm going to wrap up this lecture so that at least you understand some of the concept that we dealt with, and when you were not there. Right. The molecules, I'm just wrapping this up, or the molecules, they do occupy volume. They do fill up the space of the container in which they are confined on. We are saying that the molecules do occupy volume because we have said that matter is anything that occupies space and display the properties of mass and inertia. Because there is nothing, whether visible or invincible, in this planet, as long as innerly mass, it occupies volume. Because there's nothing innerly mass is weight, and everything innerly weight, innerly mass is matter. Therefore, no matter what, it has to occupy space. But because the molecules, and the molecules is a what now? Is a combination of the atoms in a fixed ratio through chemical reactions. We are therefore saying that those molecules, they do occupy what? Volume. Volume being able to fill up the space of whatever that you are confined on. We are saying that when pressure is high, when pressure or pressures are very high, when the pressure is high, when the pressures are very high, the molecules are compressed. We are saying that these molecules, they are compressed. Now the Putagorna didn't need that when the molecules, they are being pressurized, the molecules are being compressed. If Rinka, an example here, the wheel of a tire, and we try to pump an air inside air molecules inside of that motor tire, when the pressures are very high, the molecules are compressed. Is it a fact? Is this a fact that when the pressures are very high, the molecules are compressed? Do they compress one another as you are increasing the pressure? How we increase the pressure? Kamoli. The molecules that they say they become compressed. Is it a fact? I understand. Real. When the pressures are very high, the molecules are compressed. Re increase the pressure by pumping more air. And then when we pump more air, where's the halanga pressure? Ya increase. Again, how pressure increase? Come on, the molecules are compressed. Is it a fact? Yes, it is a fact. It is a statement of logic. Something that we can understand because we interact with that phenomenon on a daily basis, and not so long in our everyday life. So come on, the volume, the volume of the molecules, the volume of these molecules becomes significant. So when the pressures are very high, the molecules are compressed. We understand that. The volume of the molecules becomes significant. What does it mean when we say that the volume of the molecules becomes significant? Volume being what? Volume being these molecules filling up the space of the container that they are confined inside. Again, this is what we call volume. So come on, you have these air molecules inside of a container and they have filled up the container, the volume. Now, when they are being pressurized, when the pressure is higher and these molecules are being compressed, we are saying that the volume of the molecules become significant. The volume becomes significant. What do we mean when we say that the volume of these molecules becomes significant? The volume of these molecules becomes significant. The volume of the molecules becomes significant. Volume. This is something that fills up us. Thus, for example, this marker fills up with this. I place this marker inside of that container. Again, I want to know how much of this can fit into that. Again, that's volume. Again, so when we say the volume becomes significant, what does it mean inside of a wheel of a tire? When we say that the volume of these molecules becomes significant at high pressure. If it means that the volume becomes more, you mean to tell me there becomes more of these molecules inside of that container. More of these molecules will fill up the space of that container. Therefore, we are saying that the volume of the molecules becomes significant. Is that what we are saying? Logic, yes, statement is saying, so that we understand when the pressures are very high, the molecules are compressed. How do we increase that pressure? By adding more air molecules inside of a container or the wheel of a tire. Yeah? And by doing that, what are you doing? You are increasing the pressure because they will be colliding with one another and with the side walls of the container. Okay? Right. Come on, they press on one another, meaning they become compressed. Okay? Right. Now, the volume of these molecules that are inside of this container in terms of volume becomes significant. What do we mean by that? They become more and more. Again, the air molecules becomes more and more because you are increasing their number. By increasing the pressure, you are increasing what now? The number of effective collisions that are happening inside of that container. Therefore, by increasing that volume, you are making that significant. Why? Because now there will be more of these molecules colliding with one another and also with the side walls of the container. So when you are increasing at very high pressures, the volume of the molecules becomes significant. It becomes larger, it becomes bigger, it becomes more and more. Okay? Right, hauna taba. Right. Reberiaka. We are saying that this means that the total volume, available for the gas molecules to move is reduced. And collisions becomes more frequent. and collisions becomes more frequent. However, we have a beaker. Here is a beaker. And we want to increase the pressure of these molecules by doing what? By pumping more air. Suppose these are the molecules. I am increasing the pressure by allowing more molecules to fill up the container. Okay? So by doing this, what is going to happen now? We are saying this means that the total volume available for the gas molecules to move is reduced. The total volume available for the gas molecules to move is reduced, and the collisions becomes more frequent. By allowing more air molecules inside of this container, what am I doing? I am limiting their movement because there will be minimum amount of space, again, for these molecules to move. Therefore, they compress one another because now pressure has increased as a consequence of it allowing more air inside of this wheel tire. This means that the total volume available for the gas molecules to move is reduced. This is true. This is very true. To say that this means that the total volume available for the gas molecules to move is reduced. Their movement is reduced, and the collisions becomes more frequent. They frequently collide with one another. Why? Because there's no more space for them to move freely. And that by doing that, we talk about expansion as we grow in physics. We talk about thermal expansion. What is going to happen to that wheel tire? It will expand, dependent on the type of material that it is made up with. Okay? It will expand, and then at one stage it's going to explode. Okay? But movement of these molecules inside of the container where they are confined in is reduced, and the collisions becomes more frequent because they no longer have enough space to move freely. I don't know if it is making sense. Right, haunata. Bebari horona. This causes the pressure. We are saying that when this is happening, this causes the pressure. This causes the pressure of the gas to be higher. To be higher than what would be expected. Than what would be expected for an ideal gas. For an ideal gas. In order to understand this statement, where we dealt thoroughly with this ideal gas versus the real gases. We made a comparison or a contrast or a difference between those two at different temperatures and what so on. We dealt with this in the first tutorial. This causes the pressure of the gas to be higher than what would be expected for an ideal gas. But this statement will not make sense when, because you will require the first lecture where ideal gas and real gases were thoroughly dealt with. My duty is to give you a link so that you can make sense of the first and the second tutorial. Right. Now let us try to look at the graphical representation. Volume versus pressure. And then what are we saying that? More. We are saying that gases deviate from ideal gas behavior at high pressures. Now, this is the graph that we will get. and alright, this will be for an ideal gas, and this would be for a real gas. So what are we saying there? We are saying that gases deviate from ideal gas, from an ideal gas behavior at high pressures. So come on, gentlemen, we are saying that when the pressure is higher, there's a difference between the behavior of an ideal gas and a real gas. Now, have a share. This is pressure and this is volume. And when we are saying that gases deviates from ideal gas behavior at higher pressures. Now, we have a real gas and we have an ideal gas. So how real gases deviates from ideal gas? We simply mean real gas deviates from an ideal gas at what? At high pressures. Now, have a share. As we increase the pressure, as we start, as we increase, as pressure increases, volume decreases because they are of inverse proportional relationship. Video thoroughly we dealt with this because this is an inverse proportional relationship. When one increases, one decreases. We can see that as pressure increases, volume decreases. I guess graphical. But what we are saying, Monaco, ideal gases and real gases deviate on their behavior at high pressure. So as you are increasing the pressure, there's something, there's a deviation between the real gas and the ideal gas. Now, having a share, bona high pressure is low. This is an ideal gas. This is a real gas. Right, we can see that at maybe pressure arrays 5 kilopascal. We have a corresponding volume, mole 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So something is happening, maybe more than 45. Already, when the pressure is low, bona real gas, volume UD. But when you look at an ideal gas, volume is one fat. But let us try to increase the pressure. As we increase it 5, 10, 15, 20, 25, 30, 35, 40, however 45. Bona with a volume. Volume at its lowest. And a monana volume ebata ele kaudimo. Bona lema volume nentele kaudimo, volume nentele ka fats. Volume nentele ka fats, volume nentele kaudimo. So there is this deviation. But graphically looking at this, mona babua at high pressures. But graphically looking at this, it seems like even at low pressure, maybe this graph it's already drawn at high pressure. Maybe it was already, this graph is drawn already at high pressures. Why? Because if this is low, already at low pressure, there's a deviation. But the statement just says so now, gases deviate from ideal gas behavior at high pressure. So the graphical representation it's already drawn at high pressures. So we should not be deceived to think or even at low pressure, there's still that deviation. Because this graphical representation is at high pressure. There's a deviation between ideal gas and a real gas. So we are at low pressure and then we are increasing. No, it was already scientifically observed in the lab at high pressure. This is very, very important. Highly and highly important. Because as I interpret visual, it will seem as if even though at low pressures, there's already that deviation, a violator in statement they say, because it's at high pressure.
And you but you ever able to for like your conclusion?
In this thing.
Your guesses deviate from ideal guesses.
Hey, but how about
For what state conclusion for that graph?
for that graph? Over one is also concluded.
Guesses deviate from ideal guesses.
Measure, that's your conclusion. Guess what statements they say? Guesses deviate from ideal guesses behavior at high pressure. One is. Number 2. Six. Oh. Aksana space, siwa. Why bona? Aksana space, siwa. Jole hakisana space. Kannete ke re ho wena ha ke sana space. Why ke sa o fe chance ya o khopha? Ke kopa ho live statement e se etsa sense. This causes the pressure of an ideal gas to be higher than what would be expected for an ideal gas. Now, ke kopa ho sheba statement e se saying this causes the pressure of the gas to be higher than what would be expected for an ideal gas. So the pressure of the gas, I'm going to show you the real gas. The pressure, the real gas. How about this causes the pressure of an ideal gas to be higher than what would be expected for an ideal gas. How do you pressure mo? Pressure mo? Choose pressure mo? Real gas. Le pressure ideal gas. Why vary the pressure? This causes the pressure of the real gas to be higher than what would be expected for an ideal gas. Is it higher more, the pressure of the real gas when compared to the pressure of the ideal gas? Based on this? Yes. That's very true because it above the ideal gas. It above. So come on, the pressure of the real gas is higher than the pressure of an ideal gas, because we expect the pressure of the ideal gas to be above the pressure of the real gas, but that is not the case. The pressure of the real gas seems to be higher than the pressure of the ideal gas at high pressures. That's exactly what we see. The pressure of an ideal gas is higher than the pressure of an ideal gas at higher pressures. But what we expected, the pressure of the ideal gas to be above the pressure of the real gas. But unfortunately, this is not what we are observing. Hence, the statement is saying this causes the pressure of the gas to be higher than what would be expected for an ideal gas. This is just what we are saying. Gases deviate from ideal gas behavior at high pressures. And then I want to emphasize the fact here this is drawn based on high pressures. Not worry, we are starting at low pressure and then we are increasing as we are moving to the right. No, this is already drawn at high pressures. We can see that there's a deviation between the real gas behavior and the ideal gas behavior at high pressures. But we didn't expect that. We honestly didn't expect that based on the first tutorial that we had. Right, now how to the second thing. The second thing. The forces of attraction do exist between the molecules. The molecules still have this force of attraction that binds them together as a molecule. As a molecule. Just because old bonds are being broken and new bonds are formed, that doesn't mean that the forces that hold the molecules together are destroyed. No. For the fact that you were an atom, a reactant, and then you became a product by breaking old bonds and forming new bonds, the forces of attraction are still there, holding the very same product of a molecule as one. Hence, we are saying the forces of attraction do exist between what? The molecules. My father, the molecules. The molecules. At low temperatures, when the speed of the molecules decreases, obviously, because at low temperature, the molecules are low kinetic energy, obviously. At low temperatures, when the speed of the molecules decreases and they move closer together, the intermolecular forces becomes more apparent. Again, they become more apparent because they tend to have more power on holding the molecules because their temperature and their speed is low. At your weakest. Jesus, attack at your weakest. Only on point. The problem is how you can never and ever always be on point, on a charm. There has to be times when you are at your weakest so that you can remember your creator. My father. Right. As the attraction between the molecules increases, their movement decreases and there are fewer collisions between them. The pressure of the gas at low temperatures is therefore lower than what would have been expected for an ideal gas. If the temperature is low enough, if the temperature is low enough or the pressure high enough, a real gas will liquefy. And this is very true. We're going to explain why this is so. And then graphically we will also try to interpret that. Forces of attraction do exist between the molecules. Forces of attraction do exist between the molecules. Right, at low temperatures, when the speed of the molecules decreases, at low temperature, the speed of the molecules is at its weakest and they move closer together. At low temperatures, when the speed of the molecules decreases, and they move closer together, the intermolecular forces becomes apparent. At low temperature, when the speed of the molecules decreases, come on, Tomang, at low temperature, the speed of the molecules is low and the molecules move closer together. So, come on, Tomang, when they move closer together with alanga intermolecular forces study, they become more apparent. They are more stronger at that point. When the temperature is low and the movement of the molecules is restrained, lower, the intermolecular forces becomes more apparent because they are moving closer to one another. So come on, the intermolecular forces that holds them as a molecules becomes apparent. This is making a lot of sense based on the kinetic theory of gases. Again, we looked at that in the first tutorial, and a man was not there. Jesus was not there. As the attraction between the molecules increases, their movement decreases, obviously, because they cannot now move freely because of the intermolecular forces that holds them as one. So we are saying that as the attraction between the molecules increases, their movement decreases. Their movement decreases and there are fewer collisions. And there are fewer collisions between them. I don't want to bring in the Boltzmann distribution curve more because I don't know why. As the attraction between the molecules increases, their movement decreases and there are fewer collisions between them. So come on, Jama, because there are fewer collisions between them. Come on, Jama, they will not be interacting with one another frequently. So come on, Jama, there is no possibility of a chemical reaction that can transpire because they need to collide with one another with good orientation and angular and all that. We will deal with the valence shell electron pair repulsion theory some other time, where we clearly state and specify, or as the number of collisions increases, frequent number of collisions based on the Boltzmann distribution, there is a higher chance of a chemical reaction, and old bonds will be broken and new bonds will be formed. But remember, here we are just looking at gases where there is no chemical reaction that is happening. Chemical reactions, that relationship, pressure and volume, which also in a sense deals with the chemical reaction. But let's not bring in the reaction when our old bonds are broken. Let's just leave that out. Let's just look at the molecules that do occupy volume. Some other time. So as the attraction between the molecules increases, their movement decreases and there are fewer collisions between them. Boyles name, but right, the pressure of the gas at low temperature is therefore lower than what would be expected. This is what we are saying. We are saying that the pressure, of the gas, at low temperatures is therefore lower than would be expected. for an ideal gas. If the temperature is low enough or the pressure high enough, a real gas will liquefy. If the temperature is low enough or pressure, because remember we are speaking of an inverse proportional relationship, or pressure is high enough, a real gas will liquefy. This is what we are saying, because there are three states: liquid, solid, and gas. If you are a gas and you liquefy, you become a liquid. If you are a liquid and then your temperature is decreased, you do what now? You become a solid, based on your relationship between pressure and volume. So this is what we are saying. We are saying that the pressure of the gas at low temperatures is therefore lower than would be expected for an ideal gas. If the temperature is low enough or pressure is high enough, because this is an inverse proportional relationship, a real gas would liquefy. My father, you want to liquefy a gas, either increase the volume and decrease the pressure, or decrease the pressure and increase the volume. One of those two, if it is tempered with in an inverse proportional relationship, a gas would liquefy. That is and then graphically, this is what we are saying. Graphically, you have your pressure and then you have your temperature. And then what are we saying? This would represent an ideal gas. And then another real gas, and there is this deviation. This is a real gas. When we look at pressure and temperature, temperature is on the x-axis as an independent variable, and pressure is on the y-axis as a dependent variable. So there is a direct proportional relationship between pressure and volume when it comes to an ideal gas. As the pressure increases, the temperature also increases. But there is this deviation when it comes to a real gas. This is what we are saying. We are saying if the temperature is low enough or pressure is high enough, a real gas would liquefy. It will change from the state of being a gas to a neutral state of being a liquid. It would liquefy. These are the scientific facts that you should state when it comes to the theoretical approach of a real and an ideal gas. And unfortunately, this is all what I have prepared for the day. I just wanted us to complete the first tutorial with the second tutorial, so that tomorrow we can deal with something else. Kapa, we can go and deal with the previous question papers based on this, so that we understand it clearly, what revolves around this. So, how can you prepare in science? The chapter is 11 prepare for Hosani, so that I can deal with that.